New VNA Calibration Verification Board. This board is used as a golden measurement standard to assist signal integrity engineers using vector network analyzers. Measurements will be made with a Shockline Anritsu 4-port VNA. This demonstration video will show the features and benefits of the board and show how to verify calibration is accurate of your VNA. We'll also use a beta line to calibrate the VNA to make impedance and accurate cursive measurements and show a setup to determine differential probing bandwidth. The basic feature of the circuit board is that it has a 70 gigahertz PCB bandwidth. It is RF connector dependent. You can add a 2.4 or 1.85 and get a 67 gigahertz board. We have probe to connector traces, connector to connector traces, and impedances varies between 50, 100, 85 ohm, and a beta line where we can add custom impedances or traces. Some of the benefits of using this board is that you can verify that the VNA is calibrated accurately and to detect measurement drift. The traces can be an excellent tool for teaching new VNA users, and you can learn how to calibrate the VNA to measure time impedance and frequency domain S parameters.
Has this ever happened? I calibrated my VNA, connected to the device under test, but the measurements aren't correct. I bet this newly purchased VNA is broken. I am never going to rent or purchase from that company again. I'm going to call and threaten to return it, or have the sales guy drive 3 hours to show me how to calibrate and use this darn thing. Wait! You say there can be some functions left on the VNA that can show false measurements even though I calibrated it? All I need is a golden VNA calibration standard to troubleshoot my setup? Tell me more.
Hi, what we're looking at today is a verification board from DVT Solutions, and they're nice boards to verify your calibration on your VNA. And the way that you would use those is you would load the S parameters of the board back into the VNA and compare your measurements of the board versus the data that's provided by DVT Solutions, and see if the data looks good. The other thing you can do is you could characterize the board yourself after one of your calibrations and compare it, save that file, and then compare it moving forward with your VNA measurements as well. So maybe your frequency plan is slightly different, then you can use a new set of files. But the good thing is you have a board that's standards, and you can compare the data, saved data, versus the new calibration data. So if your system drifts for any reason, you can come back and actually measure the board and compare it to the data before to see if it's changed. If it has changed, then of course you need to do a new calibration. If it has not, you can assume your calibration is probably good. So there are things that go bad with instrument setups, and maybe you haven't reset all the parameters completely, or maybe somebody has used the system and has come back and you're taking data and it doesn't look very good. You can grab one of these boards and take a look at that data and see if it still applies. There's a couple of gotchas in VNAs that don't get turned off. For example, if somebody was making measurements that can affect your calibrations or your verifications. One of them might be a reference plane extension. So if somebody was doing a calibration or making a measurement on a board, they may have applied reference plane extension to it. And I'll show you what that looks like if they do. So we're looking at both the good board versus the S parameter data that we took with that board. And I'm just going to move the reference plane extension now and look at the real data, the good data we put into memory. So we're going to just move the reference plane 5 millimeters, for example, and now you can see that the data has changed or is deviated from where it was before. So if I see a condition like this, then I know I could have something wrong with my setup, or I just could have a bad calibration and I need to go back and recal. Another thing that's quite often found as in setups is the de-embedding. Whenever you're working with a structure, or somebody has de-embedded a fixture or a line, sometimes they forget to turn that back off before they do a calibration. If you run into a situation like that, it's going to look similar to this one. I'll check. We have a network that we have pulled in from a USB drive, and we're going to apply that now to the measurement. So now there's a structure in there that's says it's being embedded, but it's really not. So I can verify the fact that this board is not performing the same. So now I know again, well, I either have a setup problem or I have a bad calibration. I need to go back and recal. So these boards are very good for verifying the calibration that you've done, maybe in a previous cal, and you want to verify that it hasn't drifted or that I don't have anything incorrect in my setup.
Next, we're going to use the Shockline to perform a low-pass harmonic calibration to measure impedance on the Betty line. And we're going to calibrate our cursors to measure distance.
Okay, as a reference, as going back into looking at these particular lines, I've connected the VNA now to the Beatty standard line that's on this board. And I'll walk you through the setups for that standard, so it kind of helps you as an aid to get through the setup measurements for the low-pass time domain. Okay, so now we're looking on screen of an S21 measurement and an S11 measurement of a Beatty line. So a Beatty line is basically a 50 ohm transition to a 25 ohm transition back up to a 50 ohm transition. So it's in a single-ended mode. So we're looking at S11. So that is the basic response of a Beatty standard. Depending on the quality of the Beatty standard, it could be more rounded or less rounded, depending on how well the material has been designed. So anyway, we're going to take a look at it in time domain to see if we actually do get a 25 ohm drop in the impedance. So to get into that menu, we'll select display. We're going to go into impedance mode. So we're going to look at impedance magnitude so we can read the ohms directly off of the standard. So go into time domain. So we're going to select low pass time domain so we can look at it as if we were looking at it with a TDR. We're going to look at the range to make sure our range is set up. You can see now that we have the connector. There is a line length there. Here's two mismatch lines, and then there's some more connection that goes on, and then we're looking way out in the distance. So we'll move our stop to about 35 centimeters. And we're working right now with air dielectric because we use K connectors on the boards. And so this is what it's going to look like with the air dielectric. And this is what we do in impulse mode. So we want to actually look at this in step mode so we can identify it as a TDR type response or give us actual impedance and values and be able to tell easily whether it's inductive or capacitive. So now we're looking at the Beatty standard. So this is the Beatty standard in air. And I can then put markers on there and take a look at the marker values, for example, and see if they are close. So the 50 ohm line is here. 2 lines down, you can see 25 ohms is going to be between these two, and that's exactly where we are. I can take a look at it with a marker. So I'm going to turn my reference marker off for now. And I'm just going to look at marker 1. And I'm going to drag him to the middle of that line. So I'll drag him to the middle of that line. I can see that he is 25 ohms. Okay. Now I want to know is my distance is correct. So is it really a 25 millimeter line or not? So I can turn my reference marker on, and now I can move him to the beginning of that line, that juncture, that 50 ohm step. And he's there, and then I can move my reference line over on the other side. And I'm going to take a look, and I can read up here now the delta between that, and it says, oh, look, it's only 4.5 centimeters. But on the DVT board, they tell you what the dielectric constant is of that board, so I can now set that. And I can come back over here to here, go to user defined, and I can enter their value, which is 3.55. And then I can set up and take a closer look at those distances. So now I can see that it's 24.32, so I probably didn't get my markers exactly in the right spot. So an easy way to do that would be to go back into impulse mode. And I can see that they're just a little bit off, so I could adjust those. And then I can go back in step mode, of course. So now I can see I'm probably closer to the actual values. So the dielectric and the measurements are going to be pretty darn close. And you can check these also against the simulated data as well. So that's looking at it low pass. It's an easy way to train yourself and get up to speed in making measurements in time domain, for example.
Using the probe test pads to connector traces, verify probe system bandwidth, test different probe de-embedding techniques, and learn to set up the VNA for single or different. Here's an example of a probe to connector board. The red lines show where the probing lines would be. Here is a picture of a 40 GHz Anritsu Shockline VNA connected to two differential GigaProbes probing the differential probe to probe traces to extract time and frequency domain data.